So we finally made it to the last section here in chapter 8. We're going to split it up over 2 days. So we're going to look at the cross product of vectors here. So we already know how to add vectors, subtract vectors, find the angle in between vectors, whether they're in 2 dimensions, whether they're in 3 dimensions, do the dot product, and do vectors in space. Okay? Cross product's going to be the last operation we're going to do with vectors. So cross product is basically just a vector that's orthogonal to any 2 vectors in space. Okay, so you take 2 vectors, an A or a B. All the cross product is the resulting vector will automatically be perpendicular to whatever 2 vectors you have. Okay, so you can take 2 vectors in space anywhere. They're going to make a plane. Okay, and you could tilt this picture and pretend the plane's like that. So cross product will give you the orthogonal vector there. So cross product only works for vectors in space, not 2-dimensional things. Okay? Here's how we do it. Now I know the formula looks a little overwhelming. Okay, it's not something you have to memorize, you just have to know how to use it. We're going to use matrices for it and determinants. So you probably were exposed to them in college algebra, but we're going to need a quick little review of those guys here. How we designate it is with an X. Okay, make sure you don't put a dot there because that would be a dot product. So a cross product, we're going to use an X. So you have your I, J, and K components for vector 1 and for vector 2. Okay, we're going to do the determinants of these. So basically all this formula right here is if you want to find the resulting I components, you literally go to the I's and you cross these out this way and that way. This remaining 2x2 matrix is what the I's are. B1, C1, B2, C2, and all you do with those, multiply on diagonals and subtract. Okay, B1, C2 minus B2, C1. So you're just going to get it set up and then you're just going to perform the operations. Now, the formula has one wrinkle in it, and that's this little minus sign here. So after you do your first determinant, you move over to the J's. So you cross the J's out. The 4 remaining things form your new 2x2 matrix, A1, C1, A2, C2. Again, cross multiply and subtract, starting with this diagonal right here. So these 2 things minus these 2 things. There's your J component. Lastly, you move over to the K component. So you cross out the K's. This 2x2 is what's left, and you cross multiply, and this one's separated by a plus sign. So set everything up, put some marks in there, write everything out, and that's how we're going to find them. Okay? So let's take this guy here, and we'll run through one example together. Now, you need to be showing all your work, all your setup, because if you miss a negative sign, it can really screw things up. And I want to try and give you as many points as possible, but I also can't look through every single little step you're doing here, so make it easy on me and show the work. Okay? So I want to do the cross product with these guys. Now, it shouldn't matter what order I do this. So V crossed with W should be the same thing as W crossed with V. So we're going to take the V matrix right here, 2, 3, -1. We're going to take the W matrix down here, -1, 2, -1. If you want to see a full setup for this, here's what it would look like. So start with this matrix here, and then you can take a pencil or just rewrite it and cross these guys out. I usually just cover it up with my finger. There's the I's. Now remember, the formula of that thing is a subtraction. Okay? So we cross out the J's. The last one is an addition. We cross out the K's. Okay, so first step is you set all that up. Now we multiply on diagonals and subtract. So -3 minus -2. Make sure you write all that out. These guys get multiplied, these guys get multiplied and subtracted. Minus -2 minus +1 plus 4 minus -3 in the k. So this is how you'd write your final answer for it. -I plus 3j plus 7k. Remember, what that resulting vector is one that's going to be perfectly orthogonal to whatever plane those two guys make in space. Okay? Now, there's a lot of proofs you can do with these to kind of come up with some different algebraic formulas. So what if we just let some vector u be some generic a1, b1, c1? Okay? If we want to cross u with itself, some interesting things can happen. Okay, I'm going to pause this guy right here and get it all set up. If you guys want to try that, I'll meet you just after the break. So I wrote two vector u's on top of each other because we're crossing it with the exact same thing. These are just going to be generic variables here. Okay, so we could easily give them values and do u cross u, but obviously that only works for those specific things, so we generalize it with the variables here. So if you cross out i's, you're left with these four. Cross out j's, you're left with a's and c's. You cross out k's, you're left with a's and b's. It's always minus plus. Okay, now go ahead and do the discriminants for these. I'm again going to pause it and we're going to see what happens. So I took out the little sub ones there because they're all really the same thing. So I'm just calling them variables a, b, and c now. So when you do discriminants here for these, you notice you get the exact same thing. So those will cancel, give you 0i. This will give you minus 0j, and this will give you plus 0k. So basically, when you take a vector and you cross product it with itself, you should get 0. Because how can you take a vector and make something perpendicular to it if the two vectors don't make a plane? Leads us to these properties here. Okay? We've already looked at this one. If you do u cross v, it's the negative of v cross u, just so you get that perpendicular vector going in an opposite direction. With scalars, it works the same way. You could do a cross product first, or you could apply the scalar to just one of those and do a cross product, or to the second one and do a cross product. It's probably easier to do this first and then just make everything bigger. And then lastly here, let's say you added two vectors together and then did a cross product. What happens is, in this case, you can distribute. So u cross v plus u cross w. I would rather do this first because vector addition is pretty easy. And then you just have to do one cross product. Because if you do this one, you're doing a cross product here, which is 6 total determinants, which can lead to a lot of mistakes. Okay, so we'll pick up here in part 2 and kind of finish up with a few things about what cross products let us do.